In our chapter on miscellaneous TLS topics, we have reached the last topic, which is to investigate the differences between the master secrets, pre-shared keys, and encryption keys, and the pseudo-random function PRF and the HBAC-based key derivation function HKDF. As we will get to understand shortly, the protocol design of TLS fundamentally evolves around the goal to have the client and the server authentically agree on these secrets, from which the keys used to protect the application data exchanged later on can be derived. This lesson is now about investigating the relationship between the master secret, pre-shared key, and encryption keys within TLS 1.2, where this relationship is given by the pseudo-random function PRF. The ultimate goal of TLS 1.2 is to have the client and the server arrive at keys that can be used to encrypt and authenticate the application data exchanged later on in the TLS connection. The keys used to encrypt and authenticate later application data are derived with the pseudo-random function PRF, which is defined in RFC 5246 and which we will have a look at on the next slide. The default starting point for the derivation of the encryption and authentication keys is the pre-master secret. The pre-master secret is a variable length bit string which is established by means depending on the key exchange specified by the cipher suite that was agreed to be used between the client and the server. If an RSA-based key exchange was specified, then the pre-master secret is locally generated by the client and then sent from the client to the server by means of the client encrypting the locally generated pre-master secret with the public RSA encryption key contained in the X509 server certificate. The server, being in possession of the private RSA decryption key, can then obtain the pre-master secret by just decrypting the encrypted pre-master secret sent by the client. Besides an RSA-based key exchange, also an ECDHE key exchange could be specified to be used between the client and the server. In case of an ECDHE key exchange, the pre-master secret is then almost straight out just the result of the ECDHE key exchange conducted. The RSA-based key exchange and the ECDHE key exchange can now be used in conjunction with a pre-shared key, and in case a pre-shared key was used in conjunction, the pre-shared key is then simply mixed into the result of the RSA or ECDHE key exchange to form the pre-master secret. Again, the pre-master secret is a variable length secret whose length depends on the key exchange conducted. From the variable length pre-master secret, TLS 1.2 then uses the pseudo-random function PRF to derive a fixed length 48-byte master secret. If a client and a server would decide to resume a previous session, then the client and the server would reuse the master secret that was established in the previous session. From the master secret, the keys used for the encryption and the authentication of the application data exchanged later on are then derived again by using the pseudo-random function PRF. What's quite cool is that within TLS 1.2, both the client and the server get their own keys, both for the encryption as well as the authentication, and the number of keys to be generated then depends on the actual ciphers used for the encryption and the authentication. That's it. This derivation tree outlines the relationships between the pre-master secret, master secret, encryption keys, and authentication keys, and from this derivation tree we can see that the link between these secrets and keys is given by the pseudo-random function PRF. It's now clear that this pseudo-random function PRF is of highest importance to TLS 1.2, so let's have a closer look at it. The TLS 1.2 pseudo-random function PRF is defined in RFC 5246 and is essentially a repeated application of the hash-based message authentication code HMAC. HMACs require a cryptographic hash function, and the cryptographic hash function used within a TLS 1.2 connection is the cryptographic hash function specified by the cipher suite that was agreed to be used between the client and the server. Looking now to the left side of this slide, we can see that the TLS 1.2 48-byte long master secret is derived with PRF from the pre-master secret, plus additionally also the client and the server randomness that the client and server exchanged by means of their respective hello messages. From this master secret, a key block is then derived with PRF, and the derivation again makes use of the client and the server randomness exchanged. The lines 9 to 16 then outline how the pseudo-random function PRF really is just a repeated application of HMAC, with the results of these repeated HMAC applications then concatenated together to form the key block. The key block is then split into various parts to be used either by the client or the server, where the individual parts then form the encryption key and the authentication key used to protect the application data exchanged later on. It's quite instructive to exercise this derivation on an example, and an interesting example is given in case a client and server agree on a cipher suite using AES CBC with 192 bit keys and SHA-256 for HMAC and PRF. As both the client and the server require an AES CBC 192-bit key and a 256-bit HMAC key, a key block of length 896 bits is required. The PRF function then uses HMAC SHA-256, and as HMAC SHA-256 produces 256-bit outputs, PRF needs to iterate HMAC SHA-256 4 times in order to get a key block of length 1024 bits. A key block of length 1024 bits is then enough to be split into the total of 4 keys, where 2 keys go to the client and 2 keys go to the server, and with each the client and the server receiving a 192-bit AES CBC key and a 256-bit HMAC key for the protection of the application data that they will exchange later on. With this, I covered all I wanted to say regarding the TLS 1.2 pre-master secret, master secret, pre-shared keys, encryption keys, and the pseudo-random function PRF. Myself, I think the inner cryptographic workings of TLS 1.2 are absolutely fascinating, and I hope that I may have conveyed some of this fascination to you as well.